Hello everybody. Let us try to understand an algorithm which is period finding algorithm, which is an important algorithm in famous quantum algorithm known as Shor's algorithm also. So what is period finding algorithm? In this algorithm we are given a function fx equal to a to the power x mod of capital N. So what is the job at hand? We want to find the smallest positive integer r called the period such that f of x plus r is equal to f of x for all x. That means if r is therefore the function f is a periodic function with period r, basically we want, and we want to find out the period. The period finding algorithm is a core subroutine in Shor's algorithm. Factoring a composite number capital N is hard classically, but becomes efficient if we can find the period r of f of x equal to a to the power x mod n. So the key lies, the moot point or the key point lies in finding the period r of this function fx. If you are able to efficiently find this period r, even for factoring a composite number capital N, it becomes very efficient and we will be able to achieve this task in polynomial time. So as I just mentioned, classically period finding is with exponential time complexity, whereas quantumly it becomes polynomial time. So let us try to understand the algorithmic steps involved in the quantum period finding. First of all, we have to initialize the registers with a value small n. So how to find this value small n? We need to take the seal of log of capital N. So you take log to the base 2 of capital N and then apply seal. That will be your value of n. And we consider two registers. One is the input register, the other is the output register. The first register, which is the input register, let us take this register of the size equal to 2n qubits, and the second register, which is the output register, and its size is n qubits. We store x in the first register and we store the function fx in the second register. Right, that's how the setup of this algorithm is, of the implementation of this algorithm is. Now we initialize the state. So initial state will be all 0 states for the first register and the second register both, and the first register is defined by this ket 0 to the cron 2n and ket 0 to the cron n for the second register. We apply the Hadamard gate on all the qubits of the first register. So apply h to all 2n qubits of first register to create uniform superposition. So applying the Hadamard gate will create superposition, uniform superposition of 1 over under root q, where q is equal to 2 raised to the power 2n. So therefore this is the state of the quantum system when we applied Hadamard gate to the first register and the second register is the all zero is in the all zero state. We apply the unitary transformation on second register, that means the modular exponentiation, which actually computes the function fx. Therefore the state after the unitary operator is applied, the state of the system is, for the 2 register quantum system, will be ket x in the first register and a to the power x mod of n in the second register. So this is the state of the quantum system after 2 operations. One is is applying the Hadamard gate on the first register and then applying the unitary transformation, which is modular exponentiation, to find out the function fx, which is a to the power x mod of capital N. Now after applying Hadamards to the first register and then computing the function fx using this method of modular exponentiation, the total state of the 2 register becomes first register is in the uniform superposition state, and the second register contains f of x. That's the overall quantum state of the two register quantum system. Now the first register holds the superposition of all possible inputs x, and the second register holds the all corresponding function values. So that's the placement of the values in the registers. The first register contains the x values and the second register contains the fx values. Now this state is entangled. After we apply the Hadamard gate on the first register and the modular exponentiation on the second register, the overall state becomes entangled after applying the Hadamard transform and modular exponentiation. In most quantum algorithms, like Shor's algorithm, fx is a many-to-one or periodic function. So that creates correlation. So if I say that the state is entangled, so therefore that creates correlations between the registers, between the first register x and the second register fx. That means their values are dependent on each other. They are not independent. That's therefore we say that the states are the overall state is entangled. So different values of x typically give different values of fx. So the sum ket x and ket fx cannot be written as a product of the state of first register and the state of the second register. That means they are not separable states. The ket x and ket f of x are not separable. They are entangled with each other. They are paired up with each other. Their values depend on each other, right? So the failure of factorization is the hallmark of entanglement, right? Is the hallmark of the entanglement. Now, since the two states are now, two registers are entangled, or the overall quantum state is entangled, we measure the second register. Now, before measuring anything, the system is in this entangled state, as I have just described. Then we measure the second register. This means that every input x in the first register is paired with its output fx in the second register. This is because of entanglement. There is a perfect correlation between registers. That is, if you know fx, you would exactly know which x it came from. So that means if they are entangled and if you knew fx, so you would exactly know from which x the fx value has come. So that's the importance of entanglement here. Suppose you measure the second register and observe f of particular value of x naught, and you observe that the value the second register contains is y. So this just means amongst all possible output, your measurement showed the value y. Quantum mechanically, measurement does two things. It gives you a classical value. So the classical value it gave, let us say, is y when we measure. This is particularly the case when we measure the second register, and it gives us a value y. And it collapses the entangled state. Of course, when we are measuring the second register, it will collapse the overall entangled state, removing all terms which do not correspond to that result. So we say that the overall state is entangled. That means the state of the register 1 is dependent on the state of the register 2, and vice versa. They are entangled, they are paired. So therefore, if I find a value y in the second register during measurement, of course the state will collapse after doing the measurement. Secondly, this is very important. This just means amongst all possible outputs, your measurement showed the value y, as I just described. Quantum mechanically, measurement does two things. One is that it gives you a classical value. The second thing is very important. It collapses the entangled state, removing all terms which do not correspond to that result. So the second register contains y. The first register which earlier was the uniform superposition of all the x's, of all the x values, then this since the state has collapsed, the first register will contain only those values which correspond to the value y in the second register. So once you try to measure second register, the overall entangled state will collapse. It gives you a classical value in the second register, but in the first register, those values will survive for which which are related to y, which are so removing it will remove the collapse will remove all the terms in first register which do not correspond to that result, which is y. So what survives after collapse? Only those x values survive for which fx is equal to y. So this is an important point. For those values of x will survive for which fx is equal to y. So the first register shrinks to a superposition of only those inputs that map to the measured value y. So this is the moot question: where does periodicity come in? We are dealing with a periodic function, so our function is a periodic function. That means the values that map to the same output from a the values that map to the same output come from a sequence x0, x0 plus r, x0 plus 2r, x0 plus 3r. So we can put here the values that map to the same output. We can write here actually come from a sequence. So this is the sequence which will collapse for which the value in the second register will be y, and that sequence is x0, x0 plus r, x0 plus 2r, x0 plus 3r. Now the first register collapses to, so therefore the first register will of course the first register will collapse, but the first register will collapse to, now j is an index here, right, and the state is x0 plus jr. And what is m? M is equal to the floor of q. Q we know it is equal to 2 raised to the power 2n minus x0. So what is x0? The starting point such that fx0 plus fx0 is equal to fx0 plus r. That's the starting point. So q minus the starting point divided by the period. So that is value m. So therefore our first register will collapse to this state, right, where r is the period, q is the total size of the first register, m is the number of values in the collapsed state, right. This value helps normalize. So this is actually, this value of capital M will help the overall normalization of the state. So let us take an example in which q is 256, x0 is 3 and r is 4. So therefore m will come out to be 63. Now the state we can write like this: the state of the first register after collapse is given by this. Hence the QFT is applied to extract the period. So that's here the QFT is applied to extract the period. Now once again, if we look at the algorithm says that first of all we will have to put all possible x values in superposition. So the register contains all inputs at once. Now evaluate fx, right? So then we evaluate fx on that superposition. Now and the pairs will be formed like, now pairs like x plus r are entangled to the same output. That's important. We measure the second register, so that collapses. We measure basically the second register also and the first register also, right, where let me come to, yeah, this means that the measurement of the first register will be like, let me just come to the sequence. Yeah, this is the sequence in which the first register will be there, and since both the registers have collapsed, both the registers have collapsed, right? Both the states in both the registers have collapsed. The second register will have a value y. The first register will have those values of x for which map to y, right? And this is the sequence that maps to y, right? So therefore, in general, we can write the state of the first register to be ket of x naught plus jr, and of course m comes from q minus x naught by r. So therefore, this result gives you a value related to r, right? So apply the QFT to this periodic superposition, right? Once you apply the so after you get this sequence, right, apply the QFT to this periodic superposition. So this is your let me write here, this is your periodic superposition. Apply the QFT to this. Now what will happen, this applying the QFT will give you that collapses will give you spacing in x, right? So therefore, what do I mean to say is that this step of when we apply, hence the QFT is applied to extract the period. So after the first register is collapsed to this state, you apply QFT, right? So what it will do, applying the QFT will convert the spacing in x. The spacing in x means the r is the spacing in x. So applying the QFT to this periodic superposition converts spacing in x into peaks in frequency, right? So this result gives you a value related to r. So that is the period of this function, and this is so from that you compute r using the classical maths. So once you have reached to the value r, then you can measure the classical value. Classically you can measure the value r. So QFT is applied to bring the spacings in x into peaks in frequency. So that is the point to be understood. That's the job of quantum Fourier transform. Thank you.